guys take notes? What were you doing the whole time? Not getting paper? You have to put your phone away. Thank you. Here we go. Get these definitions down, please. First thing. This is binomial distributions. Sorry. Sampling distributions. Sampling distributions.
It's different than the other, obviously.
Sampling. So, parameters. When we're talking about parameters, we're talking about numbers that describe a population. We've already gone over this, so just a quick review. Parameters are numbers that describe a population. So everybody. Oh, I have that there. So it's a fixed number. And we don't really, which is the funny thing, because we spent almost the first semester talking about the parameter being mu and sigma. But in reality, we never really have those numbers. It doesn't make sense to really have those numbers. Because if we had those numbers, then we wouldn't need statistics in the beginning, right? We wouldn't need to take samples, find statistics, X bar and S, if we already had parameters. Those are the ones we're trying to find, okay? But for the purpose of learning the course, sometimes we make assumptions that we know what the parameters are in order to practice. So, may I move on?
No.
Cool. Kobe Jack? I love Kobe Jack. Okay. The other word is statistic. Statistic is really what we work with. And statistic are numbers that describe a sample. So it's a few of the population. Okay? It's not everybody. And of course, those numbers are not static. They can change depending on what your sample consists of. Okay? If I have this classroom, I call this my population, I can find an exact average age, I can find an exact average height. That number would be static. It wouldn't change because you guys are it. But if I grabbed a few of you guys, maybe 10 at a time, the average of those first 10 could be different from grabbing another set of 10. Okay? So that number can change depending on the specific sample that you've drawn. And that's what this is saying. And of course, we often use it to try to estimate a parameter. Any questions on those two slides?
Wait, please.
So is it always just the average?
What do you mean?
Like, if you took the 10 people and you took the average of whatever you chose, is it always going to be an average, or?
It depends on what you're finding. It could be a proportion. It could be something else.
Okay.
So it's either going to be an average or a proportion of it.
you have the PowerPoint slides on like the website?
No, but I can put them on here. Make a note. Okay. So here's a comparison between the two. Over on the left side, you're looking at parameters. On the right side, you're looking at statistics. When we're talking about a mean and a parameter, we use this symbol. It's a Greek letter mu. While over here in statistics, we actually use this symbol x bar. That's how you know the difference. If they give you a mu, you're talking about a parameter. If they give you x bar, they're talking about a statistics. Yes, they both are averages, but talking about two very different things. Standard deviation, sigma versus S. If we're talking about proportion, which is the other thing you're talking about, good stuff, is you can have a P, and P hat is actually P with a little hat on top. Okay, that's a P hat. So if you see P, then that's a true parameter, while a P hat is a statistic. It's a sample. And these are also words that will give it away. If you're talking about the true mean, then it's a parameter. And it said, oh, the sample mean, then you would know that it's a statistic. You gotta lie, I take it. Questions here? Cool. Moving on. Sampling variability. You have to understand that when we're talking about statistics, and like we said earlier, if you're talking about a sample mean, the sample mean can change. Okay, it's not a fixed number, and it's due to this concept here, this idea of sampling variability. And I think I used the example earlier. This class is the population of third hour AP Stats. If I wanted to get some information about you guys, and I just drew, grabbed like 10 of you guys at a time, that mean of that specific 10 could be very different from grabbing a different set of 10. Okay, and so it just really depends on the luck of the draw. Okay, I could have gotten maybe these 10, or it could have been those 10, or this set of 10, or this set of 10. So there's a bunch of different possible means that can come from this population. Okay, the fact that that number changes or moves around is due to this idea of sampling variability. Because if I grab a sample of 10, record that mean, throw you guys back in, shake all the names around, grab another 10, doesn't mean I'm going to get the exact same mean again. Okay, why? Maybe instead of drawing Jose, I drew Brianna in this case, and maybe heights are a little bit different or something. I don't know. Whatever it is I was looking for. So sampling variability has to do with that idea. Questions on that slide? The beans. Same thing with proportions. Sampling distribution. Sampling distribution of statistics is the distribution of the values taken by the statistics in all possible samples of that size. So, I think I showed you guys an applet before we went on break, where it did all, had the population, it goes sample size 10, it goes flip, 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 and then it dropped another bar type thing. So here's the idea of what's happening. A sampling distribution is the idea that I've got, let's say, all of these x's, all this information. Let's talk about these as being heights. You guys get the idea? This is all x's in here. So this is distribution of heights. Okay? So maybe I'm saying, I'm going to stick with that number 10. Sample size 10. So what I would do is I'd randomly select 10 of these. Now obviously it's not going to be random because I'm going to pick them. So I'd be like, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ever see how I just selected those 10? I did it randomly, right? I'd take those, I'd find the average height of those 10. That would produce an average, wouldn't it? Understand that? Okay. I throw them back in, I shuffle them around, I select another 10. Instead of picking that bad boy, I can't erase, can I? I pick another 10, blah, 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 and they produce another X bar. I grab another 10 from that same mix, and it just keeps happening. I'm going to keep getting these X bars. Okay? What this is every possible combination of those 10, like every single way possible, imaginable, whatever you want to call it. Okay? Down at the bottom is a sampling distribution. Okay? And I think the applet was a lot nicer for that. Let me end this. What happened? Not Star Trek. This one. Okay, so here's the idea. These are all of the raw data. If I took a sample of, let's go with 10. That's what we're doing. So here's what's going to happen. It's going to animate 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's going to give me an average of those, and there's the average there. Okay? So what happens the next time I do it, those 10 points, Sam, go back into the distribution. It's going to grab another 10 again. Can any of these original 10 be picked again?
Yeah.
Exactly. It can be picked again. So here's what happens. We redo that. We draw another 10. Boom, 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 boom. That produces another mean. So we can keep doing that forever. We'll do it 10,000 times. And what happens is you're going to end up with something that has every single possible combination of 10. And that's what you're looking at here would be the sampling distribution. These are x's, while this is composed of x bars. X bars. Everyone understand the difference between the two? Cool beans. So let's get back to here. Current slide. So continuing. Okay, so I think this was drawing 2. So let's say I had just digits from 0 to 9. Now I'm drawing 2 digits at a time. Okay, so I've got digits from 0 all the way to 9. I'm going to draw 2 of them at a time. I'll find their mean. I'm going to graph that, and then we're going to take a look at that distribution. So here's every possible way, right? I can grab 0 with 0, 0 with 1, 0 with 2, blah, 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 blah. There's a whole distribution. So what I have are all these means here. And if I graph them, that's what the distribution looks like. Okay? It is nice, right? Because what does this look approximately? It looks approximately normal, doesn't it? And if it's approximately normal, then we have tools that we spent a big chunk of our semester working with, okay? Which was the normal distribution, the z-table, which is what we really want to be able to use at some point. Let's take a look here. Oh, this one's fun. Television executive and companies who advertise on TV are interested in how many viewers watch a particular television show. So according to the 2001 Nielsen ratings, Survivor 2 was one of the most watched television shows in the U.S. during every week that was aired. Suppose that the true proportion of U.S. adults who watched Survivor 2 was 37%. Okay? Now I understand the difference between a mean and a proportion? Okay? You guys remember how we have 2 types of data, right? We have quantitative. I think I spelled that wrong. And what was the other one? Good. Qualitative. Okay, if we have quantitative data, then we can find the mean and we can find the standard deviation, correct? Because those are numerical things, we can do math with those. But when we have qualitative data, we can't find a mean or standard deviation, but what we can find is the proportion of them, right? Oh, 5 of the 6 people like Snicker bars. 2 of the 3 chew on Dentine ice or something. So over here what you would use is this thing called P, which is just a proportion. Okay, and it's simply just a fraction. How many successes? I would say 5 in this case out of the 6 total or whatever. So it's just a proportion. And that proportion gets turned into a decimal because, well, can we do 5/6? Let's do 3/5. What would that be as a decimal? 0.6? So that's what that's giving you. That's telling you that proportion. So it's 37% of population watch Survivor 2. Questions there? No? Cool beans. Moving on. Okay, what this is doing is this is kind of setting up the idea of your sample size. So let's say we did a survey with 100 people. And suppose we did this 1,000 times. How many surveys do we have here?
10,000?
No, 100. No. No, you would have 100. No.
Oh my lord.
Okay, so here, take a look again. We did a survey with 100 people. Okay? So we did 100 people at a time, and we did this 1,000 times. So here's what's happening. I'm going out. I've got my stack of surveys. And how many surveys do I have with me that time? I have 100 surveys with me. And I make sure all 100 surveys get done. Okay, so that's a stack of... So there's my stack of 100 surveys right here. Boom. What do I do the next day? I got another 100. Okay? So I got another 100. Here's my other 100. How many times do I do that 100 surveys? I do it 1,000 times. So ultimately, how many surveys do I have? I have 100,000 donuts. Okay? Cool. So you understand what we're doing here? Good.
Oh, nice.
Now here's what's happening. There's the distribution right there. There's the distribution of all those surveys that we have. According to this, what's my mean? It's your ribs. 37. The average is your ribs. It's 0.37. What did we say the true mean was? 0.37. So does it look pretty much accurate? It does look accurate, doesn't it? So it was 100 people, and we did it 1,000 times. Let's take a look at this example. Television executive and companies who advertise on TV are interested in how many viewers watch a particular television show. According to 2001 Nielsen ratings, Survivor 2 was one of the most watched television shows in the U.S. during every week it was aired. Suppose that the true proportion of people that watch Survivor 2 is a 0.37. We survey 1,000 people, and we do it 1,000 times. Okay? Do you see the difference between this survey and the last survey? In the last survey, how many people, I went out with a stack of how many? 100. This time my stack is 1,000. And I'm going to do 1,000 surveys 1,000 times.
So there's more surveys less times.
Same number of times. More surveys. I did it 1,000 last time as well.
Oh, okay.
But last time I only did 100 surveys. This time I did 1,000 surveys. Question.
I'm lost.
Found you. You're right there. Where in the world is JP? He's right there.
I'm a big dude.
Okay, so what's your question?
You said they're the same amount. You're doing it the same amount of times.
Same amount of times because we did the survey how many times? 1,000 times. Okay?
Different amounts each time.
But it was last time. How many surveys did I take with me?
100.
It was 100. But this time instead of 100, now I'm carrying 1,000
At a time.
at a time.
Instead.
So I'm doing 1,000 times. While last time I was doing 100 surveys 1,000 times. Okay? How do I expect that to change my distribution? Any ideas?
Well, you could have
Well, there's more data points.
more accurate because it's more.
Well, here, not necessarily more data points because how many times am I doing it?
1,000.
I'm doing it 1,000 times. Because what I'm doing is, like the first time I took the 100, I found an average of those 100, right?
Yeah.
So if I had 1,000 means, how many means will this distribution have? it will have 1,000 as well. What I changed was simply how many of those surveys were in the stack,
So
weren't they?
it would make it more accurate because there are more surveys.
How would it make it more accurate?
Because that average is like a more accurate average because there are more surveys.
Because there could be that one guy that comes around every single time and takes
Well,
more.
let me show you a picture here, okay? Let's see if I can do this over here. Here's the first time I did it. Sample size was 100. How many X bars are in this bad boy? How many? There's 1,000. There's 1,000 surveys in here. The second time I did it, my sample size was 1,000. How many X bars are in here? It's still 1,000. So does one have more points than the other?
No, but.
It doesn't.
But when the 1,000, if you're taking a sample from 1,000 or whatever, I feel like the mean would be more to the theoretical mean than if it was only 100, so it would be more accurate.
Well, the other one was at 0.27 as well.
Would the data points be closer together to the mean? So would there be less variability?
Nice and loud.
There would be less variability.
Less variability. That's exactly right. So if you take a look at this, there we go. So take a look here. Here's the first distribution, where my sample size was 100. Carenza? Okay, so here's 100 sample size. Do you see how there's more variability between them than over here? Look at the variability there, where sample size was 1,000. So if you want much more accurate results, or I should say less variability, then what do I need to do with sample size? Increase it. If I decrease sample size, then I'm going to get more variability. Does that make sense to everyone?
So increase sample size.
Increasing sample size will decrease variability. The spread will decrease. Okay? Notice over here it went from 0.37 all the way up to 0.22. That's a lot of variability. While the second time around I went from 0.37 to 0.31. So less variability. Increase sample size, decrease variability.
So I was right, but it just.
Yeah, I wasn't just waiting for you to get there,
Oh, okay.
but someone jumped the gun on you. You were there though. Questions on this? Variability business? Jamil? You look like you're super focused over there. Either that or you're sleeping. With your eyes open. Alright, cool. Tumbling toast. A piece of toast falls off your breakfast plate. Is it more likely to fall butter side down? Murphy's Law says yes. But science correspondent Robert Matthews, Robert Matthews says that the height must be typical so that the toast has time to rotate before landing. So Mr. Matthews tests his claim by arranging 150,000 students in Great Britain to carry out the experiment of tumbling toast. Assuming the scientists are correct, and the proportion of toast that will land butter side down is a proportion of 0.5. What does that mean? Half the toast lands butter side down. Okay? Oh, what? Was that it? What did I mean to do with that? Oh, I guess it was just the proportion. So it is half. 0.5 means half of them fell butter side down. Okay?
But so this is was that a qualitative type of thing?
Yes, this is qualitative data. This would be because what's the two categories?
You can't really measure.
What were the categories here, right?
Either it falls,
side down
face
or not
down,
butter
or.
side
Right, butter side down, not butter side down. So I think that's what the point here was. What's that?
Are we supposed to find out
Cipher.
like in the assignment, are we supposed to find out what P is?
Sometimes you will, or just interpret it. What's it mean? What's it really saying? So I think that's what the purpose of this was. What is P really saying here? What is P? Now is P a? Thank you. Is P a statistic or a parameter here? Okay, the way they wrote it definitely is a parameter, right? Because is it a P hat? No, it's P. Truly, it really is a P hat. Okay, because let me ask you this question. Truly is a P hat. Because did they tumble every piece of toast possible? Did they get the entire population of buttered toast? No. Okay, so truly, it's a p hat. You see how we never really have a parameter? Can we ever really flip or tumble every piece of buttered toast? No. However, because the sample size here was so large, what do you expect to happen with that variability? Yeah, if it was at 1,000 last time, it was only like 2 bars. Then with 150,000, then I would expect it to be maybe 1 bar in both directions, which is pretty much the true P. Does that make sense? Because my sample size was so large, this P hat, I don't expect it to be any different than the true P. Okay? Hurry up time, guys. Today's a weird day. Okay, cool.
Like every other one.
I think we already talked about this. But you need to know these rules. Here we go. Variability of a statistic. Please know these rules. The variability of a statistic is described by the spread of its sampling distribution. This spread is determined by the sampling design and the size, of the sample. Larger samples give smaller spread. Here's the rule, guys. As long as the population is much larger than the sample, at least 10 times as large, then the spread of a sampling distribution is approximately the same for any population size. As long as the population is much larger than the sample, at least 10 times as large, then the spread of a sampling distribution is approximately the same for any population size. I don't know what that means. Okay, here's what it's saying. Let's say I did 10 times n. That has to be greater than the actual population size. Population. Now, here's the deal. Do I really know what the population is? Do I really know how much toast is out there for me to butter and do this experiment with? I don't. So here's what you need to do. In my sample, how many toasts did we have out there? 150,000. So if I take 10 and I multiply it by 150,000, I'm just gonna add a 0, aren't I? Okay. Do you think that there is more than 1,500,000 toast out there in the world? Yeah. Okay. So that means that I can actually use, and I'll give you a formula later for that, this formula for determining what the variability is. Okay. So everyone understand the rule? As long as the population is at least 10 times as large, then you can say we're good.
But you really don't know how.
You really don't know, but surely there's more than 1,500,000 pieces of toast out there. You're right, yeah, and that's how the professor said you would choose to say. Surely there's more than 1,500,000 pieces of toast out there.
But you
Buttered
can't
toast.
really prove it.
No, but it's kind of like, okay, I don't really have to prove it. I know that there's more than that, right? So for example, if I was talking about Coca-Cola, I don't know. If I was talking about Coca-Cola, and I wanted to find out how much Coke they actually put in there, and let's say I use a sample size of 50. Okay? So if I used 50 Cokes to do that, do you think there's more than 500 Coke bottles out there?
So if you had
Sure.
500 Coke bottles, then you could pretty much say how much Coke is in the bottle based on the 50 that you had.
Right. Because surely there's more than 500 Coke bottles, correct? So that means that I can use my standard deviation formula. Okay? Cool beans? Okay, unbiased statistic. And we talked about bias and unbiased before as well. Okay? Do you guys remember how when we had a distribution, let's say that's the mean, we'll call this, actually let's call that the true mean. Okay? If I've got a distribution that has this, that looks like that, is there bias to this statistic? Yes, why? Because the X bar is not right where the mu is, right? So, an unbiased statistic means that you would have, gosh darn it. That means that you would have the same mean as the population. Okay? How do we know that? We don't. Which is kind of crazy. That's why we do statistics. But that's what they're saying when it's unbiased statistic. They're saying that the parameter would be equivalent to the statistic. Tough concept to wrap your mind around, especially since we don't know what the true parameters are. Can I move on here? Okay. I can wait too. Change it now? Can I change it now? Kobe. Okay. Here's a couple of pictures we're going to talk about. And then we'll talk about what the picture we want is. Hopefully, because some people are more visual than anything. So we'll take a look at these first. Now, is this guy very accurate? Is he accurate? Is he precise?
Yes.
Very precise, not very accurate. Okay? So this has high precision, low accuracy. You understand that? Well, he's very precise. Is he accurate though? No. Where is he supposed to hit? Bullseye, right? Right in the center. So is he accurate? Inconsistent, but he's precise. Not inconsistent because they're all nice together, aren't they?
Precise means, is he left-handed or right-handed?
Okay? No, so what are you asking? Precise? He's consistent.
Consistent.
Yeah.
It's the same place.
Yeah, he consistently hits the same spot. Okay? But he's not accurate. Okay? So this is considered high bias, low variability. Okay? That means that the distribution is very tight, very close together, but it could be way off from where the true mean is at. Okay? Take a look at this picture. Is he accurate?
Yes.
Technically he is. Is he precise? No. Okay? But technically he's accurate. If we took the average of all those, where would it be?
In the center.
Right in the center, correct? So what we're saying here is that this has low bias, okay, because the means would be almost right on top of each other, but there's so much variability that it's useless. Okay? Look in this picture. That is the worst case scenario, isn't it? That has high bias, high variability. What we strive for is to get
Wait, can you go back to the last one?
this one?
That one's low bias, high variability?
Right. And I'll show you another picture so that can kind of make sense to you, okay?
How does it make it biased?
Because, no, this has low bias. So what this is saying, let's say this was that's the true distribution, okay? Can you see that, okay? What he's doing is he's got all this distribution. See that variance? That's crazy, isn't it?
So the closer they are,
But the middle would be the same. Okay, so he's accurate. He's got that low bias because his mean is the same as the true mean. However, the distribution that he has is much larger. The spread is way bigger compared to the true one. Okay, so that's what we're looking at there. Over here, we're saying, hey, you know what? This is the true mean, but bro, yours is over here. Okay, that's way off. Does that make sense?
it's like a transparent.
Yeah, because he's way off from
Spread,
his point.
but just
Right, everything's nice and tight, but he's way far away from the target. And then here's this idea, which is the worst case scenario. Like, dude, you're just completely off. You don't get it at all.
come on.
Okay, yeah, and this is exactly what we're looking for, okay?
Dentist recommend.
So, let's take a look at this distribution-wise, okay? Here's the distributions.
Wait, so why, so the one that was spread out before was low bias, but that one's high bias?
Yeah, this was low bias because you see, if we found the average of all those, where would we be? We'd be somewhere on target, wouldn't we? Okay. So now, once we go there, let's go to this picture. Take a look at those. Okay. This is the true parameter right here, where the arrow's at. What would you call that first distribution? Is it biased?
Yes.
Yes. So that has high bias. And you see the spread there? It's a lot of spread, isn't it? So there's a lot of variability. High bias, high variability. Worst case scenario. Okay? This is high bias, high variability. Can you guys pick out the good one? B, right? This has low bias, low variability. How about this one here? What is D?
High bias,
High
low
bias.
variability.
High bias, low variability. They're nice and tight, but dude, you're way off. That's the one. Over here,
High
Low bias, high
variability.
variability.
low bias, because of course the middle of those would be right about there as well, but they're so spread out that the information is useless.
So you want them both to be low?
Okay? Cool beans. That's all we're doing today. The homework tonight, simply study those notes, because when we meet next time, quiz up. Tomorrow? Tomorrow, quiz up. Make sure you know that vocab. Make sure you know that vocab. What's up?
You got a quiz tomorrow, is that what you're doing?
Yeah, quiz tomorrow. Quiz tomorrow.
Second day.
I forgot. I got unused to this.